pleasure to be here, to be joined by so many of you in person, and a warm welcome to those online as well, to tell you today a little bit about how we're approaching biophysical characterization and developability workflows paired with our discovery efforts. So just, you've seen this slide before yesterday, but to give you a bit of an overview of where do we sit. So the biophysical characterization is represented by the protein sciences, by protein production, and biophysical characterization divisions. And we work very closely with our discovery colleagues, but also with our new cell line development division that you'll hear all about in a few minutes. So I don't think I need to tell you the relevance of this. We've heard it many, many times today and in the past few years, but we do know that our first efforts are driven by biology, and when we try to optimize for functionality and push for affinity, we often start tweaking and messing with other properties, namely charges, for example, which, whilst we are improving functionality, we might not necessarily be improving the biophysical properties that will then have an impact in our ability to turn these molecules into actual products, so in terms of their manufacturing, stability, etc. And the danger of this, as also we've heard, is that it might lead to extended CMC timelines or even make some target product profiles simply impossible to achieve. And that's why we find that it's so important to include fit-for-purpose biophysical characterization screenings from as early as possible. And so in the next few slides, I'll try to demonstrate or to show you some examples of workflows that we have and how we are approaching at the different stages that these biophysical techniques can help you save time and improve quality. So for an early stage, as I mentioned early on, it needs to be fit for purpose, right? So at early stages, we know that the availability of material is not great, that the timelines are very short, and that we're working with many molecules. And so it is important to use high throughput methods that have very short timelines, do low consumption of material, and so it's mostly single point analysis, but that allow us to focus on key properties that can become red flags later on. So we're talking about melting, as we've heard, polyreactivity, propensity to self-interact, etc. And so this is a very general or a very simplified workflow of discovery and the different stages. And so we try to highlight using the different colors, so the protein sciences color, where do we start working with our colleagues. So at the stage of selection of the lead panel, it is important to do an in silico assessment, looking at the molecular properties and also potential liabilities that can be very quickly sorted. And once we move to have purified material, then in characterization for the lead selection, then we start including experimental assays on biophysical side by side with the functional characterization. And these are assays such as AC-SINS, polyreactivity ELISA, TM and TAG, Higgs scores, obviously the percent monomer determination using size exclusion, CESDS also for sizing, and DLS. So here we have two examples. I'm afraid to say we're part of the ELISA crew here at Rare Journey. And so we do have an in-house assay for polyreactivity against DNA and insulin, which can help us predict non-specific interactions. And also, we have developed a Hick method to determine Hick scores, because we do know these are important not only for non-specific interactions, but is also sometimes responsible for something we've heard. It's called stickiness, informally, and this can be a problem for stability, but also during process development. And so it's something we want to look at very early, and particularly for some formats, it can be even more relevant. Different examples, a few more examples are the AC-SIMS assay. Also, I won't get too much into that. We've heard about it, and it has to do, it can help us predict possible issues with viscosity, poor solubility, aggregation, etc. And looking at melting and onsets of aggregation, at this stage, we use very simplified methods. So we use intrinsic fluorescence for determination of melting temperatures and assessing protein unfolding, and also the propensity to aggregate, so the temperature of onset of aggregation using SLS. And particularly also looking at how these two correlate, right? So if we start seeing an onset of aggregation because we are forcing the unfolding of the protein, or if this happens before, then there's something that we need to consider, because there's an intrinsic propensity to aggregate. Another example, as I mentioned, was the size exclusion, so looking at the percent monomer from affinity purifications, because we know the aggregates and the presence of aggregates can have an effect on efficacy and also lead to immunogenicity. And one other method that we use to do size profiling, and we resort to this method at various different stages, is the CE-SDS, that can give us a good assessment of purity and again, highlight any issues of future immunogenicity. And that kind of is an example of some of the classical methods that we use at early stage. Obviously, each project is a project. Its format might have different needs. Not all assays might be suitable, so we're always happy to look into things, into the more specifics. For the late stage, then, we start changing a little bit how we need to look at things. So we're talking about a much smaller group of molecules, and we really want to get to know these molecules, right? So we want to understand and know their molecular properties, but also we need to understand how will they behave in time. So at this point, we start caring about their stability. And as we move towards this, then target product profile starts having a more important role. We're no longer talking very general properties, so we want to see if they can be developed, formulated into the final dosage form, or to enable a given route of administration. We heard of the trend for sub-Q. And the way we do this is by using accelerated stability studies, design forced degradation studies if appropriate, and also looking into pre-formulation. Yeah? So these studies are very helpful for developability. They're very helpful looking into possible formulation, but they also allow us to generate windows of operation, not just for formulation, but for process. And at which stages do we do this? So we start with a very simplified approach at lead identification stage, looking at the different size and charge profiling, accelerated stability, which we tend to monitor both the size and charge as well, and early pre-formulation studies side by side with the functional characterization, looking into kinetics and functional assays. And also later on, for lead optimization and in support, and I'm going to mention, Michael, the cell line division, then there's a wider set of techniques and a wider set of assays that become relevant because we're very close to CMC, so we need to start really designing that strategy and understanding what our potential critical quality attributes might be. And so we have a suite of assays designed for that. And that contains characterization under non-stressing conditions, so really profiling the molecule into all aspects, and also the as I mentioned, accelerated stability, usually by isothermal stress and also freeze thaw, but then the force degradation, shear stress, deamidation, oxidation, resilience to low and high pH during process, and very often high concentration stability. So a few examples of assays that we have in our toolbox and we use at this stage with the PEG precipitation assay. So this assay allows us to look at apparent solubility, so ranking the leads at this stage, and that can give us indication of ease to develop at high concentration. We look at, as I mentioned, the charge profiling. We use isoelectric focusing for that, and actually in this example we can see that an incubation for 2 weeks at 37 degrees, we do see the changes. So we do see the change in the profile, and that we start having new and more acidic species. In this particular circumstance, we have attributed it, and we believe this was most likely due to deamidation. So this would be a prompt to then design a force degradation study looking into force deamidation, possibly peptide mapping, to understand where it was happening. Again, for late stage and for early development stages, it is important to do the glycan profiling. It's a very common post-translational modification that can have huge impact on the mode of action. And as I mentioned early on, I mentioned the melting temperature. So at the late stage, we'll be revisiting that, but we'll be revising it with a technique that can give us a lot more insight and detail, which is differential scanning calorimetry. That is used to measure the TM. It's quite a relevant property with the unfolding, and here we have an example that a single point mutation into the CH2 region has caused a significant shift, and in this case it was not great, as we had a significant decrease in the melting temperature. So finally, I also wanted to give you an example, because I'm focusing today in biophysical characterization, but we are actually a protein science division, so we do have a strong group in protein production. And this is an example of how the two units collaborate. So how we use our mass spec facility, in this case, to support production. And in this case, we were challenged to try to generate alpha-cosylated antibodies with our regular cell line. We typically use ex vivo for this. And so we used the paper that was published in 2013 that makes use of CNG2FF reagent to remove fucosylation. So we decided to try by adding it to our cell media and see if we could generate alpha-cosylated antibodies. So this is the peptide mapping. I do not expect you to find any difference here, okay? This was just an illustration. But I did wanted to show you, or try to show you, there is a shift. It's a very small mass, and so it's difficult to spot graphically. It's very well done by the software. And so again, I don't expect you to see the numbers, but there is a shift from here to here. This is mass to charge, so we're talking about very, very, very small masses. And we were able, using for all conditions above 50 micromolar of the use of this reagent, to completely abolish fucosylation. And I haven't shown here the data, but there was no impact on yields or cell viability. So it was just a brief example of how our analytical capability can support different areas and different areas of the business. But bringing us back to the developability and the biophysical characterization, I do hope I was able to give you some examples of how we are addressing this at the different stages. So at early discovery, focusing on custom screening cascades using high throughput methods with low consumption and fast analysis that really focus on key properties. And at the later stage, with workflows that are tailored to project's target product profile, focusing on helping you design an efficient CMC strategy, and also including a lot of the stability that we didn't look at early on, and in early development with QC workflows that support stablecoin selection. And with this, I just want to say thank you all for your attention, and if there's anything that you believe we can help you with, please get in touch. It will be our pleasure to support you. Thank you.